In today's video, we are going to discuss stuff concerning synthetic routes, organic chemistry, which involves conversion of compounds from one stage to another involving reagents and reaction conditions. So first of all, this particular concept is at times most confusing because we don't really know the tactic how to handle it. So before I commence, I want to first of all mention some things that you always have to take note of whenever you visit a question involving synthetic routes. That there are basically two things you'll be looking at. We'll look at the first one, preparation of members of a homologous series. So if we talk about the preparation, we mean how members of each homologous series can be prepared. And number two, we're going to talk about the reactions of members of that particular series. So these are the two fundamentals that should be taken cognizance of whenever we want to deal with synthetic route, because once we've understood this concept, we will be able to treat synthetic route with ease and without confusion. So let's dive right into the display. From the display, we are going to be making analysis and making all depictions necessary. Let's move into it. So this is a layout of the synthetic route. So from here, we are going to go step by step from each compound to the next. We try to identify reagents and reaction conditions for each of the following conversions. So you can pick up a piece of paper to take down all relevant information as we are going to be moving along with the stuff. So let's begin with compound A. The identity of compound A is a haloalkane, and it is called bromopropane. And now it is being converted to a certain compound B, which we first of all don't know, but there is a reaction condition alongside a reagent used to convert bromopropane to B, compound B. So this is sodium hydroxide in aqueous medium, and in this type of reaction, the OH group from sodium hydroxide replaces the bromine in bromopropane, thereby giving rise to an alcohol. And since the OH group is negatively charged, it means that it is electron rich. It is called nucleophile. And since the OH group replaces the bromine in order to form compound B, which is an alcohol by identification because of the reagent, we are going to say it is called nucleophilic substitution reaction. Nucleophilic substitution because it is a nucleophile that replaces another species in a substrate. So should in case you're doubting as to whether B is an alcohol or not, you can choose to go to the next product that is formed from B. And if we look at this one, B gives rise to an aldehyde. And if this is an aldehyde, we realize that this is acidified potassium dichromate. And potassium dichromate is an oxidizing agent which causes compound B to undergo oxidation. So maybe I never knew what B could be, like dangling between alcohol or different compound. I can now move from B to F and realize that this is an aldehyde, and it is called propanal. So for an alcohol to be converted to propanal, there must have been removal of hydrogen, and removal of hydrogen is oxidation, which is caused by potassium dichromate. So it makes me understand that B is an alcohol, and compound B is a primary alcohol, which can be oxidized to an aldehyde. For secondary alcohols, they are going to be oxidized to ketones. So therefore B is an alcohol. Now we have already identified this guy from B, so F is known. So let's see how the alcohol, this is propanol, can be converted to an alkene. We have here an alkene before us, which is propene. So what could be the reagent required to convert an alcohol to propene? In order to convert an alcohol to propene, oxygen alongside hydrogen is removed. So water is removed, hence the name dehydration. So in order to dehydrate an alcohol to an alkene, we need to react it with concentrated sulfuric acid at a higher temperature of 180 degrees Celsius. This is the temperature that will favor complete dehydration of an alcohol to an alkene. So this is propene. Now, when this alcohol does not have the sufficient temperature to be completely dehydrated, it undergoes partial dehydration. And when it is partial dehydration, the temperature is not up to 180 degrees. It will be the same reagent, concentrated sulfuric acid, but now the temperature is going to be 140 degrees Celsius. If it is 140 degrees Celsius, it is partial dehydration, giving rise to an ether formation where there is a doubling in the number of carbon atoms. And this ether is called dipropyl ether, because we have a propyl group here, and this is also a propyl group. Since there are two propyl groups, that is 3 carbon atoms, it will be dipropyl ether, or it can also be called propoxypropane. So when B, which is an alcohol, undergoes partial dehydration, it gives rise to an ether. So this reaction is called partial dehydration. Now let's come back to A. What could be the reagent and reaction condition to convert A to C? We realize that A is converted to C by the removal of the bromine and 1 hydrogen to give rise to propene. So 1 bromine has been removed and a hydrogen atom also has been removed. So what could be the reagent? The reagent here is a metallic hydroxide as well, but what changes now is the solvent used. In order to convert bromopropane to an alcohol, we use the metallic hydroxide in aqueous medium. Now, if you want to convert it to an alkene, that is to make it undergo elimination reaction, you react in the presence of a different solvent, which is an alcohol, where the OH group from the metallic hydroxide will act as a strong base to be able to extract a proton from an alpha carbon. An alpha carbon is a carbon closer to the functional group carbon. So the alpha carbon is this carbon atom. So an OH group will extract a proton from here, since it becomes a strong base in this reaction. So we expect to have sodium hydroxide, we put in alcohol, and then we reflux. We are going to have dehydrohalogenation, removal of bromine alongside hydrogen, and this reaction is called elimination, because some species are removed from the compound to give rise to the new compound. That is why it is called elimination. Now let's look at conversion of A to G. We realize that compound A has 3 carbon atoms, but moving to compound G, it gives rise to 4 carbon atoms. So something has taken place. There is an increment in the number of carbon atoms, and whenever you see an increase in the carbon atom number, and you also see nitrogen, you think of the addition of a cyanide group. A cyanide group is the CN. If the cyanide group replaces a halogen, it is going to cause an increment, and that is one fundamental way of increasing the length of a carbon chain, or of ascending a homologous series. So the reagent and reaction condition necessary for these are, we have potassium cyanide in alcoholic medium, and the cyanide group will act as a nucleophile which replaces bromine in bromopropane, giving rise to a nitrile. So when we open up this structure, we are going to have this compound, and this is 1, 2, 3, 4, but propane is 1, 2, 3. So therefore there is an increment in number of carbon atoms, and this is a nitrile, and the name is butane nitrile. Since it's a nitrile and it has 4 carbon atoms, it is called butane nitrile. And the reagent we said here is potassium cyanide in alcohol, and then we do refluxing. We are going to give rise to butane nitrile, and this reaction is nucleophilic substitution reaction, because the cyanide group is a nucleophile that comes to replace bromine in the bromopropane, giving rise to a nitrile. In order to convert G to I, we see that there is an increase in hydrogen number, means that hydrogen has been added, because we have the same number of carbon atoms, but hydrogen number has been added. So we think of reduction if we have addition of hydrogen, and the most common reducing agent we should ever think of is lithium aluminum hydride. There are others like sodium in ethanol, but this one is most prominent as far as reduction is concerned, and the reaction condition is dry ether. So once you react this nitrile with this reducing agent, you are going to give rise to an amine, and this one is called butylamine, formation of amine from a nitrile, reduction. Other reactions that are common where lithium aluminum comes in is the conversion of aldehyde to alcohols, carboxylic acid to alcohols, ketones to alcohols. This will act as a reducing agent. While other reagents in the reverse direction are acting, like potassium permanganate as oxidant, lithium aluminum hydride acts as a reductant. Let's look at G to H. Butane nitrile being converted to butanoic acid. So we see that there will be some oxidation because of addition of oxygen. And this reaction involves an acid alongside water. An acid and water, and you warm. So you will have acid hydrolysis. This is a type of reaction, and then you heat. We are going to obtain a carboxylic acid where the terminal carbon of the CN is going to lose the nitrogen and accept oxygen atoms, giving rise to a carboxylic acid. So this is called acid hydrolysis. Now, if the carboxylic acid reacts with soda lime, what will be compound J? We want to identify compound J. Compound J is going to be an alkane. When a carboxylic acid reacts with soda lime is a mixture of sodium hydroxide and calcium oxide. So when you mix these two, it makes the compound not to become stable. Since sodium hydroxide is deliquescent, once it reacts with calcium oxide, its deliquescent nature disappears. So it is going to react with sodium hydroxide, giving rise to sodium carbonate. You see that if sodium carbonate is formed, it means that one carbon atom has been reduced from the carboxylic acid. So the alkane that is going to be formed will be propane. So it means that the product formed is reduction in carbon by 1. So this is propane from the reaction of the carboxylic acid with soda lime. And this type of reaction, of course, is called decarboxylation, because we are removing the carbon O group, which is decarboxylation, to give rise to an alkane. Let's look at compound A, bromopropane, giving rise to propane magnesium bromide. When we react magnesium with a haloalkane, we give rise to a Grignard reagent. So this reaction is Grignard formation. And the Grignard here is the propane magnesium bromide. It is in ether. It is in anhydrous ether, giving rise to this species. So upon hydrolyzing the Grignard reagent, we can give rise to an alkane. This Grignard reagent undergoes acid hydrolysis, giving rise to magnesium hydroxide and HBr alongside an alkane. So we are going to give rise to an alkane when we react acid with water in the Grignard reagent. So this is going to be CH3, CH2, CH3. Propane is going to be the compound formed. And so that is basically what we have for this synthetic route problem. So I advise you to study a lot as far as this stuff is concerned. And most importantly, study the different homologous series individually and then now have their combined effect, because a diagram like this is always drawn from individual explanations of different homologous series. So once you've had a background knowledge about different homologous series, you can be having a good footing to handling this stuff. So if you find this video helpful, do give it a thumbs up, subscribe for more videos, share with your friends, and I wish you the best. Thanks for watching.